Okay, our next speaker, switching back to GC, is Lina Mikaliunaite from the Synovec group.
Thank you. So thank you for that introduction, and thank you to the committee for letting me share two of my research projects while I'm here. So while you heard from Rob, and if you visited my poster, I was talking more about my computational work here. I'm going to talk more about the instrumental side of my PhD. And really, I'm going to be getting into plot columns. And to really talk about the plot columns and all the work that I've done, I really have to go back all the way at the beginning of my research and in my time in Rob's group, where we were just looking at plot columns for their kind of what they usually are known for, is actually these just light boiling point analytes, and we were just trying to make a two-dimensional system. But first, so most of you are probably familiar with the well-coded columns. That's kind of what we generally use to just look at most of our things like fuels and metabolomics. The plot columns, on the other hand, are a little different. Sorry, let me figure out how this, yeah. So while the well-coded columns have this stationary liquid phase on top of the capillary, instead, in the plot columns, we have these solid phase particles that are adhered to the wall. And due to that, they have some limitations, like they can't really go high in flow rate. They were traditionally known to have some particle shedding, and so they're mostly used with FIDs and not really mass spectrometer. They also have some temperature limitations due to the fact that they never needed to really go that high. They're used mostly for gases, but they are just really, really good at this one job, is doing these low boiling point analytes. And just to kind of show you how well they really do compared to well-coded columns, I do have just a schematic I'm showing this EPA megamix separated both on an RTX 200 and a plot Q column. So these were ran at the same temperature program, just to kind of give you an example. And everything in the well-coded column pretty much comes out within like the first minute, while the plot column really allows us to separate things like carbon disulfate and dichlorobromomethane. So these very light things are actually separating out. It's giving us nice separation on some of like the isomers and all of that. And so, as I said, when we started out, we really were looking at just creating a two-dimensional gas chromatography system with the plot columns. And so where we started was just using plot on both dimensions. So using a 30-meter plot column on the first dimension and a 2-meter plot column on the second dimension, because what we wanted to look at was natural gas mixture. So here you can see how that looks, and then in the two-dimensional space, it's kind of easier to see. But we have these very, very light analytes of methane, ethane. And then what's very impressive is actually that the system does separate very nicely for isomers like isobutane and N-butane that would be pretty much impossible to separate on a well-coded column. So this was cool. But then we were like, okay, let's put in another what we consider a light sample of gasoline. And if you look at this, it's taking us a very, very long time to separate that out. And it's basically only like basically up to like C6, maybe we're like getting off in the temperature program, and then everything else just has to basically we have to stay at 250 degrees, which is the limitation of the plot column to get everything else off. And so obviously that is not what we want. And so the question was, is there some better ways to use plot columns to get these two-dimensional separations and separate both the light analytes out, but also be able to actually get like gasoline off of the column? And so this is kind of how we went about that. And this is where David Bell and Restek came in, because we were looking to actually put a plot column on the first dimension and a well-coded column on a second dimension. And the one thing about the plot columns is that they have very thick film. And so if, you know a little bit about like the beta ratio and all that, to balance that out, we just need a pretty thick then well-coded column. And so Restic made us these custom-made columns that were 2 microns, just to give us a little bit more balance. Another thing to note that's very unusual about this is that we are using a very short plot column and a relatively long wall-coded column to kind of help us with balancing it all out. And so for this, we also are using a diaphragm valve as our modulator. So just like a little bit about it is a custom-made one from Valco. And the main reason why we use it is that the diaphragm valve actually allows us to have these uncoupled flow rates, which means that we don't have to actually force the plot column to go faster than it can. And so generally you just have a one-dimensional column that's filling the sample loop and then going to waste, and then you have the aux that's pushing onto the second column. And when it gets switched, then the aux is pushing everything off of the sample loop onto the second dimension column. And if we look at these separations, they look much, much nicer. And we have now separating gasoline in first 15 minutes, really pretty much like 12. We are getting nice normal phase separation of a gasoline. Things like isobutane and butane are showing up in gasoline. And we're getting nice separations of the isomers, both in the aromatics and the alkanes. So, and then really just to drive it across, this is done now. Pretty much everything is coming off in the temperature ramp, and only like really heavy stuff is coming off at the maximum temperature. But because we do research, the next question was, well, can we do even better than that? It is still starting at 100 degrees, which is not great. So we're not really getting a lot of that, like, just temperature that we can use. And so what we decided to do from there was to inquire Restic about making us thinner film plot columns and trying those out and seeing if those would work better, if we can actually make them just still have retention, but just like not like hang on to those higher boiling point analytes as much. And so I'll show you some one-dimensional chromatograms just to kind of drive the point across of 2 different samples. So we're looking at the calibration megamix, so that's kind of allowing us to look at a more higher boiling point analytes. And then we're also looking at the refinery mix that has some lighter things in it. And so here are those chromatograms. So we have an 8 micron column, a 4, and a 2. So these are 30-meter columns. In the light blue, you have the refinery mix. In the dark blue, we have the calibration mega mix. And I'm just tracking that with the temperature program. So you can see how these analytes, the biggest difference is between the 8 and the 4, where we are kind of going down in temperature for an analyte, probably about like 30 degrees. And then the next step between the 4 and the 2, we're probably going about like 10 to 20 degrees, even lower temperature. And so just to kind of show you how light the analytes are in the refinery mix. So at the beginning, really are separating the nitrogen and methane and carbon dioxide. So those are literally gases. And then on the higher end of the calibration megamix, we're going up to naphthalene, which has a boiling point of 218. And then what's really impressive about this, like, yes, they're going down in temperature and that's cool and all, but also we're not losing the retention of these very light analytes. And so if you look at the 8 micron separation at the beginning, like, yes, they have very nice separated nitrogen and methane, but there's also a lot of space in between these. And so we figured it's very nice if we can just squish that all together, not lose a separation, but that would allow us to just get these heavier things off of it. And you can really see how, like, the methane is kind of getting closer to the nitrogen. At the 2 micron, they're still baseline separated out. And so with that, I kind of went back to the 2D, and I just started doing this. So we started out with just putting in the 30-meter columns in to get just some separations out. And we're using kind of the same system with the diaphragm valve and the same thick film, RTX 200. And just to show you how, like, a gasoline mixture looks like. So This is starting out at the 30 degrees, not 100 as before. And we are between the 4 and the 2 is kind of tracking the same thing that happened in 1D. We went down by about 10 to 20. So once I run the 8 micron column, it will be much, much more to the right side. And then for some of these heavier things, it's kind of doing very similar things. And further, I also have the calibration mega mix. So this has a lot of chlorinated and brominated analytes in it. And it's also performing pretty much the same way, but we're still having this like open space in the beginning. And just kind of to just drive this across. So before, when we went from 30 meters to 5 meters, we pretty much went from 50-minute separation to a 15-minute separation. So we're hoping that once we actually cut this column into a 5 meter and put that in, it will really push everything to the left, and we hopefully will be able to separate some of the more interesting things, not just gasoline and the refinery mix, but we are planning to hopefully run some terpene samples with it and all that, because if we can't actually separate it out, it does open up this possibility to run plot columns for when you have something that has both the gaseous and the more like liquid samples in it. And so with that, we're still working on running the 5 meter separations on this, trying on some new samples, and we still are in the process of testing out the retention time, reproducibility with these new columns as they are custom made. So we want to make sure that they are actually performing the same every single time. And then with that, I want to thank my advisor, Rob Synovec, our collaborator, David Bell, and Restec and Lithuanian Foundation for funding my research.